Okay, this video is going to talk about gas laws, and I have the 3 gas laws that will appear on the North Carolina final exam listed over here on the left-hand side. And as you can see, there's the combined gas law, this one is the ideal gas law, and then this one is Dalton's law of partial pressures. And I have some things that you need to know in order to work these over here on the right. As far as those things are concerned, right here, you need to know as you read your problems, since they're going to be word problems, that when you see liters or milliliters, that you're dealing with a volume. And then you should also know that when you see atmospheres, kilopascals, or millimeters of mercury, that means you're dealing with a pressure. Degrees Celsius or Kelvin mean that you're dealing with temperature, and then the amount, if you see moles, you're dealing with the amount of a substance. I have underlined Kelvin, and then I'm also going to underline liters up here, because when we're working some of the problems, you have to have those numbers in liters, and you always have to have Kelvin in the problem. So if you don't have Kelvin, then you'll have to convert degrees Celsius to Kelvin. And the reason I have this list here is because our problems will look like this, where it doesn't always tell you what you have. Sometimes it'll just say, it'll give you the word, but it won't tell you that that's a volume or a pressure, and you're going to have to figure that out. So to begin with, I'm working the combined gas law. And if you look underneath the video on your screen, hopefully I've given you some time indications where you should look to find certain laws. I'm going to start with the combined gas law. And what I recommend that you do is you look at the problems in terms of whether or not they have a before and after component to them. So if I read through this one, it says air in a closed cylinder is heated from 25 degrees Celsius to 36 degrees Celsius. If the initial pressure is 3.80 atmospheres, what is the final pressure? So this is a problem that has like a before and an after component to it. So the easiest thing to do, in my opinion, is to make myself a little dividing line and kind of work things out in the sense of before and after. When I do this before, it was 25 degrees Celsius, and I'm going to make myself a list. 25 degrees Celsius is a temperature. And then after, it becomes 36 degrees Celsius, which is another temperature. I'm going to call before T1 and after T2. Something else that I'm going to have to do is know that I'm going to have to convert those temperatures to Kelvin in order to work my problem. So this becomes 298 Kelvin, and this becomes 309 Kelvin for T2. And then it says the initial pressure. So that means before, my pressure is 3.80 atmospheres. And after, it wants to know the final pressure. That's what I'm looking for. So if I find myself a better marker before I go on, what we're going to do is we're going to look at my formula list that I have right here. I have 2 T's and I have 2 P's. And anytime I'm working a before-after problem, it's going to have to be this first one where I've got 1's versus the 2's. So my equation is going to have to be P1 V1 over T1 equals P2 V2 over T2, as I seem doomed to pick only markers that don't want to write. So if we go on to my third marker here, finally, what we're going to see is that I don't have all these things. If I look at my list over here to the left, I don't have any V's. Well, what we're going to assume is that the volume stays the same, and so we're going to take the volume out of this. So basically I'm working P1 over T1 equals P2 over T2. And so I'm just going to plug my numbers in. So that's going to give me 3.80 atmospheres over 298 Kelvin equals something in atmospheres over 309 Kelvin. And then we've got the solving of my problem. I've got 3.8 divided by 298. That's going to be multiplied by 309. So I will end up with a final pressure. That's 3 sig figs, and then these both have 3 after their conversions, so I'm going to end up with 3.94, and my unit will be atmospheres, ATMs. Realize that that's kind of blurry on your screen, so we'll see what I can do about that for you. I'm going to go on to just another problem, and we're going to keep working them. They're going to kind of change up just a little bit as we go. My next one, we'll try some colored pencils. It says, a bubble of helium gas. We have a volume of this near the bottom of a large aquarium where the pressure, so I've got a pressure, is this many atmospheres. The temperature is 12 degrees Celsius. Determine the bubble's volume upon rising near the top where the pressure is 1.01 atmospheres and this. So I definitely have another before and after situation. I've got a bubble that's going to rise up to the top. So in this particular problem, before, I have a volume of 0.650 milliliters, and I have a pressure of 1.54 atmospheres, and I have a temperature of 12 degrees Celsius. And then after it rises up, it wants me to find the volume. It has a pressure at the top of 1.01 atmospheres, and it has a temperature of 16 degrees Celsius. Okay, so I told you earlier that with volume, you had to have liters in certain places. Here, I could choose to leave it this way. If I do, then I'm going to have a volume in milliliters, and that's perfectly fine. Those are both in atmospheres, and temperature always has to be in Celsius. So in order to convert, I add 273, so that becomes 285, and this one will be 289 Kelvin. And if I go to my formula list, I clearly have to be with this first equation because I have 2 volumes, 2 pressures, and 2 temperatures. So my full equation is P1 V1 over T1 equals P2 V2 over T2. And it's just a matter of setting them up and matching up with my list. I'm going to make these my 1s and these my 2s. So P1 is 1.54 atmospheres. V1 is 0.650 milliliters. T1 is 285 Kelvin. P2 is 1.01 atmospheres. V2, I don't know. T2 is 289 Kelvin. And then it's time to solve. I have a lot of students that need to break this down, quite frankly, and need to be very careful with the math as far as how you're solving things. Me personally, I'm going to go ahead and simplify and do 1.54 times 0.650, divide that by 285. So this whole side is now equal to that number. I need to multiply that by 289 and divide it by 1.01. So my volume upon rising to the top, I can have 3, 3, 3, everything has 3 sig figs, so it will be 1.00 milliliters will be my answer for the volume upon rising to the surface. Now, I'm going to work 2 more problems that are all going to be a little bit different. If you don't understand how I plugged all of that into the calculator at warp speed, then that's something that you should ask me about in class, because I'm definitely assuming that people are comfortable with the math in order to do this with chemistry. And I'm going to play changing of the writing utensil again. This time, I have a sample of gas with a volume of 215 cubic centimeters at 23.5 degrees Celsius and 84.6 kilopascals. What volume will it occupy at STP? I chose some different problems that would show us some different things. This one has a different unit of volume than we're used to, but it's still a unit of volume. And again, I have a before and after problem here because it's separated into two components. Before, I have a volume of 215 cubic centimeters. I can work my problem with that. I just need to know that my volume afterwards, which it's wanting to know, will be in the unit of cubic centimeters. It's at a temperature of 23.5 degrees Celsius and a pressure of 84.6 kilopascals. What volume we have right there will it occupy at STP? Well, you have reference tables that we've been using in class, if I can get my hands on one. And if you cannot remember what STP is, remember to look here. You have standard pressure and standard temperature. Now for standard pressure, there's 4 different numbers listed. If I look at my problem, it's already in kilopascals. So I should use the one that matches up with it, which is the 101.3 kilopascals. If I use another unit, then I'm going to get myself good and messed up. Standard temperature, it went ahead and told me it was 0 degrees Celsius or 273 Kelvin, so I'm going to use that number so I don't have to do any thinking about it. And if I convert this to Kelvin, I'm going to add 273, which makes that 296.5 Kelvin and a class change. So again, if it's a before and after problem, it has to be this P1 V1 over T1 equals P2 V2 over T2. Okay, and again, I have all things going on at the same time, so I'm not going to drop anything out. I'm going to plug my numbers in, and I'm going to get 84.6 kilopascals times 215 cubic centimeters over 296.5 Kelvin. That's going to equal my other volume times 101.3 kilopascals over 273 Kelvin. And again, I'm going to go fast with the math, assuming that you're comfortable. And if not, you can ask me about it later. And then I will end up with a volume here at the end of 165, and let's see, it'll be 3 sig figs, 165 cubic centimeters as my answer for the problem. Alright, my last one should hopefully be a little bit easier if I chose wisely. And so on this one, I have an initial volume of a gas at a pressure of 3.2 is 2.9 liters. What will be the volume if the pressure is increased to 4? So I still have a before and after. Before, I have a volume of 2.9 liters. I have a pressure of 3.2 atmospheres, and they want to know what will the volume be if the pressure is increased to 4. So I don't have anywhere near as many things this time. It still has to be the same equation that we've been using right here, because I've still got 2 V's and 2 P's. So I'm going to write the whole thing down again. And I'm going to look at it and see that it doesn't mention anything about temperature on the bottom. So we're going to assume that temperature is the same. It's not changing, so we're going to take it out. So that means on the before side, the P1 and the V1, we'll call these V2 and P2, I've got 2.9 liters times 3.2 atmospheres. I did switch my V and my P as far as placement goes, and that doesn't matter. And then I'm going to have V2 times 4. So this time when I go to solve, it's 2.9 times 3.2, divide that by 4. I have a volume of 2.32 liters. This was in liters, so this will be in liters. And this has 2 sig figs, so does this, and so does this. So I'm going to have to change that to 2.3 liters as my answer. Now, if you're sticking with me, I'm going to switch formulas here, and we're going to put it all in one video. Another possible formula for me to work is the ideal gas law, and that's this one right here. PV is equal to nRT. On this one, if I read through it, I don't have a before and after. It says a 35-liter tank of oxygen is at this temperature with an internal pressure of 190 atmospheres. How many moles of gas does the tank contain? So there doesn't seem to be anything changing. There's no before, there's no after. So I'm going to go ahead and make my list still. There's a volume of 35 liters. Right here, it doesn't tell me, but I recognize that Kelvin is a temperature. So there's a T of 315 Kelvin. It does say pressure. There's a pressure of 190 atmospheres. It asks me how many moles. That's the little letter N. That's what I want to know, is how many moles. Well, if you go back to this formula over here, then I need an R. Well, on my reference table, there's a list of R values right here. There's 3 different R values that I've circled somewhere along the way in class. Match them up with the unit of pressure that you already have in the problem. On this one, it's in atmospheres. So this first one is the one that has atmospheres. So I'm going to be using the R value off my table of 0.0821 liters times atmospheres over moles times Kelvin. Yes, I'm going to write all that stuff. Whoops. And then I'm going to bump the table real good. We've already established that this is my formula. So I'm going to plug things in where they go. My P is 190 ATM. My V is 35 liters. My N, I don't know. It's what I want to find. My R value is 0.0821 liters times atmospheres over moles times Kelvin. And that is going to be multiplied by 315 Kelvin. Now, I wrote all that up there to show some of you that mathematically this does work out. The units of Kelvin will cancel out. One's in the denominator, and then I'm multiplying by 1 in the numerator if you think of it as over 1. So if I simplify, and I'll do more of the math for some folks on this one, I'll end up with 190 times 35. So that's 6,650. I'm going to keep my units. That's ATMs times liters is equal to 0.0821 times 315 is 25.8615. Now keep all the units. L, liters times atmospheres over moles. And all of that is times the letter N. I've just moved it over here to the right. If I want to get N by itself and I'm multiplying by all of this stuff, then I'm going to have to divide both sides by all of this. So when I divide by all of this, you should understand that this is the same thing as what I had before, that this really is over the top. That's going to be the same thing as multiplying by this, moles over 25.8615 liters times atmospheres. Well, when I do that, these are going to cancel, that's going to cancel, the number cancels, but I also have to do this to the other side. So moles goes on top, 25.8615 atmospheres, liters will go over here. Well, when I do that, look, atmospheres cancels, liters cancels. So I've got 6,650 divided by 25.8615. And the unit that I'm left with is moles. So I'm going to end up with N equal to, how many sig figs can I have? This has 2, 2, that doesn't count because it's off the reference table. I can only have 2 sig figs, and the number in my calculator is 257.1, so that's going to become 260 moles as my answer. Now, I've got one more of these ugly things. I have 75 liters, contains 62 moles of gas. At this temperature, what is the pressure? So I've got a V of 75 liters. I have an N of 62 moles. I have a T of 2150 in Celsius. What is the pressure? Well, again, I don't have an R, which means I get to pick one off the reference table. And this time I don't have a pressure, so I can pick any R that I want to, because whatever R I pick, it will be those units that I'm left over with for the pressure. So it really doesn't matter. So let's see what we've got here. This is 2423. We're going to plug it into PV is equal to nRT. My P I don't know. V is 75 liters. My N is 62 moles. I'm gonna pull off this middle one. I'm gonna use the smallest number as far as digits go, but actually the largest in size. 62.4 liters times millimeters of mercury over moles Kelvin. And then that's times 2,423 Kelvin. Well, this time it's a little more simple. Moles and moles cancel. Kelvin and Kelvin cancels. If we have another class change and some more division and multiplication, I will get this whole side equal to this. Well, I'm not going to write all that down. I know that I'm going to have to divide by 75 in order to get my answer. And so I'm going to end up with a very large number, but that makes sense because it's at a very, very high temperature, so that shouldn't seem all that crazy. Now, I am going to need to take the number that's in my calculator and change my sig figs. This has 2, that has 2. This one doesn't count because it's a reference number, so it has an infinite number. So I'm going to have to make this have 2 sig figs. Well, I can keep the 1 and I can keep the 2. The 4 is going to make the 2 stay the same, but this needs to be in scientific notation. So it's going to be 1.2 times 10 to the 1, 2, 3, 4, 5 times, whoops, I'm writing and talking at the same time. 1.2 times 10 to the 5th. When I divide by liters, that makes those cancel out. So I'm left with millimeters of mercury. 1.2 times 10 to the 5th millimeters of mercury for my answer. Alright. I'm going to switch these around. Dalton's law of partial pressure is next. Moving on to this equation right here, where I have the P total is equal to all of the pressures added up with each other. I've explained in class about how you collect something over water. So right here it says I have a sample of hydrogen gas collected over water at 35 degrees Celsius and 760 millimeters of mercury. What's the pressure of the dry gas alone? What this means is that the pressure, the total pressure that I have is the pressure of hydrogen gas plus the pressure of some water vapor that's with it. And if I want the dry gas, I just want this. I need to take the water out of it. So the total is 760 millimeters of mercury. The pressure of the hydrogen is what I want. And I wasn't given in the problem, but I have these little tables in my notes. It says it was collected over water at 35 degrees Celsius. Well, find 35 degrees Celsius on my little table. I will see that water has a pressure of 42.5 3.2 millimeters of mercury at that temperature. I could have chosen 5.63, but that's in kilopascals. If it's on a test for our class or the final exam, you'll have to be given this information. You're not expected to know it. And then to solve for the pressure of the hydrogen, I simply take my 760 and I subtract 42.2. So the pressure of that is 717.8. My unit that I'll cram in there is millimeters of mercury. Here's another way of using Dalton's law of partial pressures. It says a mixture of hydrogen, nitrogen, and oxygen has a pressure of this. The pressure of the oxygen is 0.567 and the pressure of the nitrogen is 0.326. What's the pressure of the oxygen? Well, it's just like last time. I know that it has to be the pressure of the individual things. This will be the hydrogen, the nitrogen, the oxygen, instead of putting 1, 2, and 3. The total pressure, it told me, is 1.342 atmospheres. The pressure of the oxygen gas is, I think I made this so you couldn't do it. We'll have to change this to hydrogen. I made a typo. Pressure of the hydrogen is 0.567 atmospheres. The pressure of the nitrogen is 0.326 atmospheres. And I'm asking you for the pressure of the oxygen. So in order to do this, we just subtract. The pressure of the oxygen will be 1.342 minus 0.567 minus 0.326. I end up with 0.449 atmospheres. These usually aren't too bad. The last one that's possible, we did in my honors classes, but not in my regular classes. I'll write the equation here. It was Graham's Law of Effusion. It was the rate of A over the rate of B was equal to the square root of the molar mass of B over the molar mass of A. And it is flipped. That's not a typo on my part for once. So if it's asking me to compare, it says find the relative rate of diffusion for the gases chlorine and ethane. Well, I'm going to compare chlorine to ethane. So if I'm going to do the rate of chlorine over the rate of ethane, I need to do the molar mass of ethane first. Well, carbon has a mass of 12 times 2, that's 24. So hydrogen has a mass of 1 times 6, so it has a mass of 30 grams. Chlorine has a molar mass of 35.5, and if I multiply that by 2, because there's 2 atoms of it, it'll come out to be 71. So I need to do 30 divided by 71, and then I need to find the square root of that. So what I get as an answer is 0.65. There's no units that go with it. It's simply a multiplier. It tells me then that chlorine is 0.65 times as fast as ethane. Well, what that means, if I have a number that's less than 1, that equals slower, whereas greater than 1 equals faster. And if by some chance it was equal to 1, then it would be the same. If I come down here, I have this question. 1 mole of hydrogen sulfide gas escapes from a container by effusion in 77 seconds. How long would it take 1 mole of ammonia gas to escape from the same container? Well, first I'm going to have to compare the two. I'm going to need to do the rate of H2S compared to the rate of NH3. Well, then that's going to be the molar mass. N is 14, H is 3, so that's 17 over 32.1 plus 2 is 34.1. So I've got 17 divided by 34.1, the square root of that. So H2S is 0.71 times what NH3 is. Okay, well if I interpret that, it's slower, based on what we just set up here, which makes sense because it's got a heavier mass. It's a bigger molecule. It's going to take it longer to come out of a tiny hole. So therefore, if it takes H2S 77 seconds, one way that I would look at it in class is I have two choices. That 77 seconds can be divided by 0.71, or I can multiply it by 0.71. If you use a little bit of common sense, basically you can think through it this way. If I know that the H2S is going to be slower, if I divide 77, and you can do it, by 0.71, I get 108 seconds. Whereas if I multiply it by 0.71, I get 54.67 seconds. I know that NH3 should go faster. Which one of those two answers makes sense? Only this one. This one's faster. This one would take even more time than the H2S. So it has to be 54.67 seconds. Now, to fly through this, if you have a random list and it's all mixed up and you have no idea what to do, then a couple of suggestions. Number one, look for a before and after scenario. If it's before and after, it has to be the combined gas law. Otherwise, make yourself a list. Like this one says, a sample of oxygen was collected over water, and it wants me to find the pressure of the dry gas alone. Both of those are clues to me that it has to be this equation right here. It has to be Dalton's law of partial pressure. They gave me some extra information to some degree. I need this to find the pressure of the water vapor, but ultimately I don't need it to actually set it up in my problem as a T. If I look down at this one, I have a container of gas with a volume of 5.6 liters and this pressure. What will the pressure be if the volume is compressed? Okay, I can recognize this as a before and after problem. And so I can start making a list. Before, it has a volume of 5.6 liters and a pressure of 1.34 atmospheres. After, the volume is compressed, and it wants to know what that will be. Oh no, just kidding. What will the pressure be if the volume is compressed to 3.4 liters? It wants to know pressure. Well, the only thing that matches up out of that is this equation. It has to be this one. And I don't have any temperature. It never mentions it, so we presume it stays the same. And I'm going to plug into this formula here. This last one has a sample of gas with a volume of this, a pressure. How many moles of gas will be in the container if it's at this temperature? Well, I don't have a before and after, so it's not going to be the formula up above. It doesn't mention anything about individual pressures. It gives me a volume of 2.34 liters, gives me a pressure of 567.3 millimeters of mercury. It asks for moles, and it gives me a temperature. It's pretty clear to me that this has to go into this equation. I've got a P, I've got a V, it wants N, I have T, and I recognize R is a constant that I can find off of my reference table. So I have it as well. So it's going to go into this equation. So look to see if you have a before and after. And then always make a list and match it up with your formulas. And then if you need more help with actually how to solve for one of the variables in a math sense, then that's something that you could ask me about in class.